Now we are going to learn about the properties of electromagnetic radiations. So let's start. Electromagnetic radiations. In classical physics, a flow of energy at the universal speed of light through free space or through a material medium in the form of the electric and magnetic fields that make up electromagnetic waves such as radio waves, visible light, and gamma rays. In vacuum, electromagnetic waves travel at the speed of light, commonly denoted as c. Electromagnetic radiation comprises electromagnetic waves which are synchronized oscillations or vibrations of electric and magnetic fields. In vacuum, electromagnetic waves travel at the speed of light, generally meant c. In a homogeneous isotropic media, the motions of the two fields are perpendicular to one another and to the direction of energy and wave proliferation, framing a transverse or crossover wave. Time-varying electric and magnetic fields are mutually linked with each other at right angles and perpendicular to the direction of motion. The electromagnetic wave is characterized by its intensity and frequency, v, of the time variation of the electric and magnetic fields. So which are the major points discussed in the previous slide? Electromagnetic radiation comprises electromagnetic waves, which are synchronized oscillations or vibrations of electronic and magnetic fields. Electric and magnetic fields, synchronized vibrations. In vacuum, electromagnetic waves travel at the speed of light, generally meant by c. In a homogeneous isotropic media, the motions of the two fields are perpendicular to one another and to the direction of energy and wave proliferation, framing a transverse or crossover wave. Time-varying electric and magnetic fields are mutually linked with each other at right angles and perpendicular to the direction of motion. An electrostatic wave is characterized by its intensity and the frequency and the time variation of the electric and magnetic fields. Radiation fields in which vectors E vector and P vector are perpendicular to each other and to the direction of propagation. Electric component and magnetic component will be there. So electromagnetic radiation is a wave of electric and magnetic field propagating at the speed of light, c, through empty space. So there will be electric component and magnetic component. Electromagnetic radiation is a wave of electric and magnetic field propagating at the speed of light c through empty space. In this wave, the electric and magnetic fields change their magnitude and direction each second. This rate of change is the frequency measured in cycles per second, namely in hertz. The electric and magnetic fields are always perpendicular to each other and at right angles to the direction of propagation. So we can see a structure of electromagnetic wave. We have mentioned a point where in this wave the electric and magnetic fields change their magnitude and direction each second. This rate of change is the frequency measured in cycles per second, namely in hertz. The electric and magnetic fields are always perpendicular to each other and at right angles to the direction of propagation. Next, we can see that wavelength is there. Then magnetic field oscillation can be seen. This is a representation of a wave of electromagnetic radiation. Perpendicular propagation is there. So electric field oscillation, magnetic field oscillation, wavelength will be represented and propagation is there. So in terms of modern quantum theory, electromagnetic radiation is the flow of photons, also called light quanta, through the space. Photons are packets of energy h nu that always move with the universal speed of light. The symbol h is Planck's constant, while the value of v is the same as that of the frequency of the electromagnetic wave of classical theory. Next, Planck's equation is equal to E is equal to hf, where E is the energy per photon, f is the frequency of the photon, and h is the Planck's constant. E is equal to hf. And after the announcement, like I have to say something, like in the video we will be just dealing with the v portion as f because that is convenient. So I will be mentioning v as f. F is equal to frequency. This is nu, which is represented in this v like thing, but due to some problems in the text we used, it just turned out to be a V. So we will be representing as that V as F. F is equal to frequency. So Planck's equation, E is equal to hf. E is equal to hf, where E is the energy per photon, F is the frequency of the photon, and h is the Planck's constant. And when we just look at the spectrum of frequencies of electromagnetic radiation, extends from very low values over the range of radio waves, television waves, and microwaves to visible light, and beyond to the substantially higher values of ultraviolet light, X-rays, and gamma rays. So what is the importance of this? All human life is immersed in it, and modern communication technology and medical services are particularly dependent on one or another of its forms. All living things on earth depend on the electromagnetic radiation received from sun and on the transformation of solar energy by photosynthesis into plant life or by biosynthesis into zooplankton, the basic step in the food chain in oceans. The eyes of many animals, including those of humans, are adapted to see sensitive to and hence to see the most abundant part of the sun's electromagnetic radiation, namely light, which comprises the visible portion of this wide range of frequencies. The eyes of many animals, including those of humans, are adapted to be sensitive to and hence to see the most abundant part of the sun's electromagnetic radiation, namely light, which comprises the visible portion of its wide range of frequencies. All the fuels that modern society uses, gas, oil, and coal, are stored forms of energy received from the sun as electromagnetic radiation millions of years ago. Only the energy from nuclear reactors does not originate from the sun. Food is heated in microwave ovens, airplanes, and guided by radar waves. Television sets receive electromagnetic waves transmitted by broadcasting stations, and infrared waves from heaters provide warmth. Infrared waves also are given off and received by automatic self-focusing cameras. Next, ultraviolet radiation, which the eyes cannot see, but whose effect is felt as pain from sunburn. Ultraviolet light represents a kind of electromagnetic radiation that can be harmful to life. X-rays, which are important in medicine as they allow physicians to observe the inner parts of the body, but exposure to which could be kept to a minimum. Next, gamma rays, which came from nuclear reactions and radioactive decay, are part of the harmful high-energy radiation of radioactive materials and nuclear weapons. The effects of EMR upon chemical compounds and biological organisms depend both upon the radiation's power and its frequency. EMR of visible or lower frequencies, visible light, infrared, microwaves, and radio waves, are called non-ionizing radiation because its photons do not individually ionize and have enough energy to ionize atoms or individuals to break chemical bonds. The effects of these radiations on chemical systems and living tissue are caused primarily by heating effects from the combined energy transfer of many photons. In contrast, high-frequency ultraviolet, X-rays, and gamma rays are called ionizing radiations, since individual photons of such high frequency have enough energy to ionize molecules or break chemical bonds. These radiations have the ability to cause chemical reactions and damage living cells beyond that, resulting from simple heating, and can be a health hazard. Generation of electromagnetic radiation. Electromagnetic waves are emitted by electrically charged particle undergoing acceleration is accelerated by an electric field. Electromagnetic radiation is produced whenever a charged particle, such as an electron, changes its velocity, whenever it is accelerated or decelerated. The energy of the electromagnetic radiation thus produces comes from the charged particle and is therefore lost by it. A common example of this phenomenon is oscillating charge or current in a radio antenna. The antenna of a radio transmitter is part of an electric response circuit in which the charge is made to oscillate at a desired frequency. A common example of this phenomenon is the oscillating charge or current in a radio antenna. The antenna of a radio transmitter is a part of an electric resonance circuit in which the charge is made to oscillate at a desired frequency. An electromagnetic wave or wave so generated can be received by similar antenna connected to an oscillating electric circuit in the antenna of a radio transmitter is a part of an electric resonance circuit in which the charge is made to oscillate in a desired frequency. An electromagnetic wave so generated can be received by a similar antenna connected to an oscillating electric current in the tuner that is tuned to that same frequency. The electromagnetic wave in turn produces an oscillating motion of charge in the receiving antenna. Any system which emits electromagnetic radiation of a given frequency can absorb radiation of the same frequency. Properties. EM radiation exhibits both wave particles and particle properties at the same time. Wave characteristics are more apparent when EM radiation is measured over relatively large time scales and over large distances, while particle characteristics are more evident when measuring small time scales and distances. Wave properties. In homogeneous isotropic media, electromagnetic radiation is a transverse wave. Any electromagnetic wave must be a transverse wave where the electric field E and the magnetic field B are both perpendicular to the direction of wave propagation. So just remember, this wave is a transverse wave with a magnetic field B and E both perpendicular to the direction of wave propagation. So transverse wave is a very important term here. A monochromatic wave, a wave of single frequency, consists of successive troughs and crests, and the distance between two adjacent crests or troughs is called the wavelength. Waves of the electromagnetic spectrum vary in size from very long radio waves longer than a continent to very short gamma rays smaller than atom nuclei. Frequency is inversely proportional to wavelength, so V is equal to F lambda, where V is the speed or velocity of the wave. C in a vacuum or less in other media. A monochromatic wave, a wave of single frequency, consists of successive troughs and crests, and the distance between two adjacent crests or troughs is called the wavelength. Waves of the electromagnetic spectrum vary in size from very long radio waves longer than a continent to a very short gamma rays smaller than atom nuclei. Frequency is inversely proportional to wavelength. V is equal to F lambda, where V is equal to the speed velocity of the wave. C is the velocity in vacuum or less in other media. F is the frequency and lambda is the wavelength. As waves cross boundaries between different media, their speeds change, but their frequencies will remain constant. When some waves just change the media, there is a major point that their speeds change, but their frequencies remain constant. So E is equal to F lambda. Then amplitude is something which represents the height. One wavelength is height to trough, crest, trough, time. Electromagnetic wave can be seen, and wavelength is commonly characterized by the symbol lambda. It is defined as the distance between two most near points in phase with one another. Hence, two adjacent crests or troughs on a wave are represented by a distance of a single complete wavelength. Velocity of EMR, electromagnetic radiation, is equal to velocity of light through vacuum into wave number. Wave number is equal to 1 by wavelength. We have learned that V into A is equal to F lambda. So lambda is something which is represented by wavelength. So V is equal to F lambda, and we just replace the wavelength with 1 by wavelength, that is wave number. So velocity of light through vacuum is the velocity of EMR is equal to velocity of light through vacuum into wave number. Wave number is equal to 1 by wavelength. Properties of wave. Wavelength. Wavelength lambda is the distance between successive crests of a wave, especially points in an electromagnetic wave or sound wave. It can be simply defined as the distance of one full cycle of the oscillation. If lambda is the wavelength, c is the speed of light, and lambda is equal to wavelength. Wavelength is the distance between successive crests of a wave, especially points in an electromagnetic wave or sound wave. It can be simply defined as the distance of one full cycle of oscillation. If lambda is wavelength, c is the speed of light, and f is equal to frequency, then we can derive the relation given below. C is equal to f lambda. The shorter the wavelength, the greater the frequency, and greater the frequency, the higher the energy. Amplitude. It is the distance from the middle of a wave to the maximum vertical displacement of the wave. Larger the amplitude, the higher the energy, and lower the amplitude, the lower the energy. So amplitude increases, energy increases. Amplitude tells us about the brightness or intensity of a wave compared to other waves. Next is the frequency. The number of cycles per second is defined as frequency. It is defined as hertz or second inverse. If E is the energy, H is the Planck's constant, which is equal to 6.62607 into 10 raised to minus 34. F is the frequency. We can derive the relation given below is equal to E is equal to H nu. Is equal to H nu or HF is equal to HF. Thus we can see the frequency is directly proportional to energy is equal to H nu. Then period. Period is commonly classified by the symbol t. It is the total time that a wave takes to travel one wavelength. Velocity. In relation to electromagnetic radiation, the velocity is normally expressed as velocity is equal to lambda v. Velocity is equal to lambda f. The wave velocity of in vacuum for electromagnetic wave is 2.99 into 10 meter per second. Particle properties. The wave model of light does not explain the several other observed phenomena like the emission of light from hot objects, black body radiation, the emission of electrons from the surface of metal when it is struck with the electromagnetic radiation, the photoelectric effect, and the emission of light from excited gas atoms like emission spectra. So we will be talking about the particle nature. Before moving on to that, let's learn what is black body radiation. When a solid is heated, it will emit radiation. We all know that. We refer to this as black body radiation because the solids appear black before they are heated. And Max Planck in 1858 to 1947 explained that a glowing hot object could only absorb or emit certain quantities of light is equal to h nu, where nu is the frequency of light and h is Planck's constant equal to 6.626 into 10 raised to minus 34, and glowing hot objects could only absorb or emit certain quantities of light. So that's about black body radiation. Next, the energy of an atom is quantized and not continuous. The change in the energy of an atom occurs when an atom absorbs or emits one or more packets of definite amounts of energy. The packet of energy is known as a quantum. The atom can only emit or absorb energy in whole number multiples of h nu. The plural of quantum is quanta. If, for example, an atom absorbs 4 h nu, we say that 4 quanta of energy has been absorbed. Planck's word quantization of energy has awarded the Nobel Prize in 1918. The photoelectric effect. When the surface of a metal is irradiated with radiant energy of a certain frequency, electrons are emitted from the surface of the metal. This is called photoelectric effect. Each metal has its own threshold frequency. The threshold frequency is the minimum frequency of light that can be used to eject electrons from the metal surface. Frequencies that are equal to or higher than the threshold frequency will cause the electrons to eject. Frequencies lower than the threshold frequency will not eject electrons from the surface of the metal. Metals have different threshold frequencies. One metal has a work function, which is the amount of energy required for an electron to overcome the attractive forces with units of kilojoule per mole. Albert Einstein extended Planck's theory of quantization to explain the photoelectric effect. Einstein postulated the beam of electromagnetic radiation used to irradiate the metal surface behaves as a stream of particles called photons. The energy of a photon is equal to Planck's constant multiplied by the frequency of light. So E is equal to h nu, E is equal to h c by lambda, where F is equal to c by lambda. We have learned that earlier. And c is equal to speed of light in vacuum, and h is equal to Planck's constant. So electromagnetic radiation is hitting on a metal and electrons are ejected. Then the electromagnetic spectra. This is something which we have heard earlier but still don't know what it is. So frequency hertz is represented, and then we can see that arrangement. Radio waves are there, television waves are there, radar waves, microwaves, infrared rays, ultraviolet light, gamma rays, and when we just separate the ultraviolet light into parts, we can see visible light is transformed into violet, indigo, blue, green, yellow, orange, and red color. So wavelength is there, photon energy h nu, electron volts is there. So we can see gamma rays, X-rays, ultraviolet rays, infrared rays, radar waves, microwaves, and television waves along with radio waves. And then the electromagnetic spectrum is the range of frequencies of electromagnetic radiation and their respective wavelengths and photon energies. The electromagnetic spectrum is the range of frequencies of electromagnetic radiation and their respective wavelengths and photon energies. The electromagnetic spectrum covers electromagnetic waves with frequencies ranging from below 1 Hz to about 10 Hz, corresponding to wavelengths from thousands of kilometers on to a fraction of the size of an atomic nucleus. This frequency range is divided into separate bands, and the electromagnetic waves within each frequency band are called by different names. This frequency range is divided into separate bands, and the electromagnetic waves within each frequency band is called by different names. Beginning at the low frequency wavelength or long wavelength. Low frequency, long wavelength. So low frequency end of the spectrum, these are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays of high frequency of short wavelength, which are the radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The electromagnetic waves in each of these bands have different characteristics, such as how they are produced, how they interact with matter, and their practical applications. Extreme ultraviolet, soft X-rays, hard X-rays, and gamma rays are classified as ionizing radiations because their photons have enough energy to ionize atoms, causing chemical reactions. Exposure to ionizing radiation can be a health hazard, causing radiation sickness, DNA damage, and cancer. Radiation of visible light and longer wavelengths is classified as non-ionizing radiations because they have insufficient energy to cause these effects. Exposure to ionizing radiation can be a health hazard, causing radiation sickness, DNA damage, and cancer. Exposure to ionizing radiation can be a health hazard, causing radiation sickness, DNA damage, and cancer. Radiation of visible light and longer wavelengths are classified as non-ionizing radiation because they have insufficient energy to cause these effects. Next, we can see a representation of this: X-ray, gamma rays, X-rays, UV rays, IR rays, microwaves, then radio waves along with low radio waves, and we will be just increasing the visible spectrum and splitting into the different colors. We can see the colors here. This diagram is represented in the increasing wavelength into the right side and increasing frequency into the left side. Types of radiation. First one is the radio waves. Radio waves are emitted and received by antennas, which consist of conductors such as metal rod resonators. Radio waves are emitted and received by antennas, which consist of conductors such as metal rod resonators. The artificial generation of radio waves, an electronic device called transmitter, generates an AC electric current which is applied to an antenna. The oscillating electrons in the antenna generate oscillating electric and magnetic fields, which radiate away from the antenna as radio waves. In reception of radio waves, the oscillating electric and magnetic field of a radio wave coupled to the electrons in an antenna, pushing them back and forth, creating oscillating currents which are applied to a radio receiver. Radio waves are emitted and received by antennas, which consist of conductors such as metal rod resonators. The artificial generation of radio waves, an electronic device called a transmitter, generates an AC electric current which is applied to an antenna. The artificial generation of radio waves, an electronic device called transmitter, generates an AC electronic current which is applied to an antenna. The oscillating electrons in the antenna generate oscillating electronic and magnetic fields that radiate away from the antenna as radio waves. In reception of radio waves, the oscillating electrons in the antenna generate oscillating electric and magnetic fields that radiate away from the antenna as radio waves. In reception of radio waves, the oscillating electronic and magnetic fields of a radio wave coupled to the electrons in an antenna, pushing them back and forth, creating oscillating currents which are applied to a radio receiver. Earth's atmosphere is mainly transparent to radio waves, except for layers of charged particles in the ionosphere, which can reflect certain frequencies. Radio waves are extremely widely used to transmit information across distances in radio communication systems such as radio broadcasting, television, two-way radios, mobile phones, communication satellites, and wireless networking. In a radio communication system, a radio frequency current is modulated with the information bearing signal in a transmitter by varying either the amplitude, frequency, or phase and applied to an antenna. The radio wave carry the information across space to a receiver where they are received by an antenna and the information extracted by demodulation in the receiver. Radio waves are also used for navigation in systems like global positioning system and navigational beacons and locating distant objects in radio location and radar. They are also used for remote control and for industrial heating. The use of the radio spectrum is strictly regulated by governments according to the International Telecommunication Union, which allocates frequencies to different users for different uses. Next is the microwaves. Microwaves are radio waves of short wavelength from about 10 cm to 1 mm. Although they are emitted and absorbed by short antennas, they are also absorbed by polar molecules coupling to vibrational and rotational modes, resulting in bulk heating. Unlike higher frequency waves such as infrared and light, which are absorbed mainly at surfaces, microwaves can penetrate into materials and deposit their energy below the surface. Although they are emitted and absorbed by short antennas, they are also recorded by polar molecules coupling to vibrational or rotational modes, resulting in bulk heating. Unlike high frequency waves such as infrared and light, which are absorbed mainly at surfaces, microwaves can penetrate into materials and deposit their energy below the surface. This effect is used to heat food in microwave ovens and for industrial heating and medical diathermy. Microwaves are the main wavelengths used in radar and are used for satellite communication and wireless networking technologies such as Wi-Fi, and the copper cables or transmission lines which are used to carry lower frequency radio waves to antennas have excessive lower losses at microwave frequencies, and metal pipes called waveguides are used to carry them. The copper cables, which are used to carry lower frequency radio waves to antennas, have excessive power losses at microwave frequencies, and metal pipes called waveguides are used to carry them. So, what are the applications of microwaves which are used in the satellite communication, used in radar, wireless networking technologies such as Wi-Fi, which we just use every day, and still we don't even know that Wi-Fi is a microwave. Wi-Fi is a microwave, which the same thing which we use in the microwave ovens and used in industrial heating. Infrared radiation. The infrared part of the electromagnetic spectrum covers the range from roughly 300 GHz to 400 THz, and an mm is equal to 750 nm. It can be divided into three parts: far infrared, mid infrared, and near infrared. Far infrared, near infrared, and mid infrared. The highest frequencies in this region can be detected directly by some type of photographic film and by many types of solid state image sensors for infrared photography and videography. Visible light. Electromagnetic radiations with a wavelength between 380 nm and 760 nm is detected by the human eye and perceived as visible light. Ultraviolet radiation. The wavelength of UV rays is shorter than the violet end of the visible spectrum but longer than X-ray. UV is the longest wavelength radiation whose photons are energetic enough to ionize atoms, separating electrons from them and thus causing chemical reactions. UV can also cause many substances to glow with visible light. This is called fluorescence. Fluorescence is something related with ultraviolet radiation. At the middle range of UV range cannot ionize but can break chemical bonds, making molecules unusually reactive. Sunburn, for example, is caused by the disruption effects of middle range UV radiation on skin cells, which is the main cause of skin cancer. Sunburn, for example, is caused by the disruptive effects of middle range radiation on skin cells, which is the main cause of skin cancer. At the middle range of UV rays cannot ionize but can break chemical bonds, making molecules unusually reactive. Sunburn, for example, is caused by the disruptive effects of middle range UV radiation on skin cells, which is the main cause of skin cancer. UV rays in the middle range can irreparably damage the complex DNA molecule in the cells, producing thymine dimers, making it a very potent mutagen. The sun emits significant UV radiation, about 10% of its total power, including extremely short wavelength UV that could potentially destroy most life on land. Ocean water would probably have some protection for life there. Most of the sun's damaging UV wavelengths are absorbed by the atmosphere before they reach the surface. The high energy, shortest wavelength ranges of UV, called vacuum UV, are absorbed by nitrogen and at lower wavelengths by simple diatomic oxygen in the air. Most of the UV in the middle range of energy is blocked by the ozone layer, which absorbs strongly in the important 200 to 315 nm range, the lower energy part of which is too long for ordinary dioxygen in air to absorb. This leaves less than 3% of sunlight at sea level in UV, which all of its remainder at the lower energies. The remainder is UVA along with some UVB. The very longest energy range of UV between 315 nm and visible light, called UVA, is not blocked very well by the atmosphere but does not cause sunburn and does not bring any biological damage. However, it is not harmless and does create oxygen radicals, mutations, and skin damage. X-rays. X-rays, which are like upper ranges of UV, are also ionizing. Due to their higher energies, X-rays can also interact with matter by means of the Compton effect. Hard X-rays have shorter wavelengths than soft X-rays, and as they can pass through many substances with little absorption, they can be used to see through objects with thicknesses less than that equivalent to a few meters of water. One notable use is diagnostic X-ray imaging in medicine, a process known as radiography. X-rays are useful as probes in high-energy physics. In astronomy, the accretion disks around neutron stars and black holes emit X-rays, enabling studies of this phenomena. X-rays are also emitted by stellar corona and are strongly emitted by some types of nebulae. X-ray telescopes must be placed outside the Earth's atmosphere to see astronomical X-rays, since the great depth of the atmosphere of Earth is opaque to X-rays with areal density of 1000 gram per centimeter, equivalent to 10 meters thickness to water. This is an amount sufficient to block almost all astronomical X-rays. Gamma rays. After hard X-rays come gamma rays, which are discovered by Paul Villard in 19,000. These are the most energetic photons, having no definite lower limit to their wavelength. In astronomy, they are valuable for studying high energy objects or regions. However, as with X-rays, this can only be done with telescopes outside the Earth's atmosphere. Gamma rays are used experimentally by physicians for their penetrating ability and are produced by a number of radioisotopes. They are used for radiation of foods and seeds for sterilization, and in medicine, they are occasionally used in radiation cancer therapy. Most commonly, gamma rays are used for diagnostic imaging in nuclear medicine, for example, in PET scans, positron emission tomography. The wavelength of gamma rays can be measured with high accuracy through the effects of Compton scattering. So, which are the major points? These are used in some techniques like PET scans and radiation cancer therapy. These are having a great penetrative ability and produced by a number of radioisotopes. They are used for irradiation of foods and used for sterilization. Gamma rays are of very important functions in our day-to-day life. Like they are very important, which are used in the most energetic photons, and in astronomy they are valuable in studying high energy objects of regions, whereas X-rays, which can only be done with telescopes outside the Earth's atmosphere, And gamma rays are used in sterilization, and they are of higher penetrating ability and are produced by a number of radioisotopes, and irradiation is happening. So radiation cancer therapy is there, PET scans are there, nuclear medicine is something which is of very important important facilities, and Crompton scattering is also there. So that's it. Thank you. Thank you for listening.